You are tuned to Iri-e-learning, and I am your host, Teacher. In this structure and bonding lesson, we will examine the properties of covalent compounds. Check the description box for links to all the videos related to this unit. By the end of this lesson, we should be able to describe the structures of covalent compounds, describe the properties of covalent compounds, and link these properties to their structures. First, we will identify the two types of covalent substances or structures that exist. They are simple molecules, also called simple covalent molecules. Secondly, are the giant structures, also called giant covalent structures. We will now examine simple covalent molecules. Simple covalent molecules or simple molecular substances are small molecules such as the diatomic molecules of the chlorine shown to the left of the screen. These simple molecules consist of strong covalent bonds between the atoms of the molecule but very weak forces of attraction between the molecules. The blue dotted lines represent the weak intermolecular forces. Note that the prefix inter means between, therefore intermolecular means between the molecules. Other simple covalent molecules include oxygen. The oxygen molecule consists of two oxygen atoms strongly bonded together by a double covalent bond, with weak intermolecular forces between the oxygen molecules. The weak intermolecular forces are sometimes called van der Waals forces. Next is water. Water contains strong single covalent bonds between the atoms of the molecule, but weak intermolecular forces between the hydrogen of one water molecule to the oxygen of another water molecule nearby. When the weak intermolecular forces involve hydrogen, they are called hydrogen bonds. Next, we will describe the properties of simple molecules. Note that the main factor affecting the properties of simple covalent molecules is their weak intermolecular forces. Simple covalent molecules have very low melting and boiling points. The illustration on the left of the screen shows liquid oxygen in which the individual oxygen molecules are held together by weak intermolecular forces as shown by the blue dotted lines. When the temperature increases, the molecules vibrate faster, eventually gaining enough energy to break free or overcome the weak intermolecular forces and escape into the gaseous state. Note that weak intermolecular forces do not require a lot of energy to break. Here is a list of 3 simple molecules that are gases at room temperature because their boiling temperatures are below that of room temperature, and average room temperature is approximately 20 degrees Celsius, and as you can see, the boiling temperatures here are all below zero because the values are negative. Another simple molecule is water. Water is a liquid at room temperature and it boils at 100 degrees Celsius and melts at 0 degrees Celsius. So simple molecules are usually gases or liquids at room temperature because the weak intermolecular forces will break very easily. Therefore, they are not sufficient to hold the molecules tightly together in the solid state. Simple molecules usually do not dissolve in water because they have no charges or ions. That is, they are non-polar. Simple molecules do not conduct electricity in any state due to the absence of charges or ions. Next, we will examine giant covalent structures or simply giant structures. Giant covalent structures are also called giant covalent molecules. Diamond, as we see to the left of our screen, is an example of a giant covalent structure. All the atoms in a giant covalent structure are bonded together by strong covalent bonds. Note that all the atoms within the diamond structure are carbon atoms. Carbon denoted by the symbol C. Other giant covalent structures include graphite, which consists of carbon atoms covalently bonded to each other. Silicon dioxide, also called silica, chemical formula SiO2, is a giant covalent structure that consists of silicon, the purple or violet circle, and oxygen, the blue circle. Notice that the structure of silicon dioxide is very similar to that of diamond, except that between the silicon atoms there is an oxygen atom bonded. Now we will describe the general properties of substances with giant covalent structures. The very strong covalent bonds existing throughout the giant covalent structures is the main factor affecting their properties. Giant covalent structures are all solids at room temperature. The reason is due to the strong covalent bonds throughout the structure that hold the atoms together. The three examples of giant covalent structures given here, diamond, graphite, and silica, are all solids at room temperature. Giant covalent substances have high melting and boiling points. The reason is they have many strong covalent bonds throughout their structures. Therefore, it takes a lot of energy to break these strong covalent bonds for the atoms to separate, causing a solid to melt or a liquid to boil or even evaporate. Giant covalent substances do not conduct electricity. This is so because there is no overall charge, neither do they form ions. Graphite, however, is an exception to this trend. We will discuss this exception in detail later on in the lesson. Giant covalent structures are insoluble in water. That is, they do not dissolve in water. They are insoluble because they are nonpolar and are unable to form strong attractions with water molecules. We will now examine the description and properties of giant covalent structures specific to diamond, graphite, and silicon dioxide, also known as silica. We begin with a description of diamond. Diamond is a colorless transparent solid that sparkles because it refracts light. Diamonds are commonly used as gemstones for making jewelry. Diamond is an element of carbon that consists of only carbon atoms covalently bonded together. If you look to the left of the screen, you will see a black circle representing a single carbon atom in a diamond. Each carbon atom within the diamond structure forms 4 covalent bonds with 4 other carbon atoms in a tetrahedral arrangement, in which the 4 carbon bonds are evenly spaced at 109.5 degrees. So there are strong covalent bonds extending in all directions. Note that even the tiniest diamond would contain millions of carbon atoms covalently bonded together in a tetrahedral arrangement. The structure of diamond consists of carbon atoms only, and the electron configuration of carbon is 2,4. Therefore, carbon has 4 electrons on the last shell. Direct your attention to the left of the screen. There you will see a diagram of a carbon atom showing its 4 electrons on the last shell. Recall that each carbon atom bonds with 4 other carbon atoms to form an evenly spaced tetrahedral structure. Notice that the central atom is bolded while the other 4 carbon atoms are not. This is done to make the central atom the atom of focus because it represents what happens with each carbon atom within the diamond structure. Note that the carbon of focus shares 1 electron with each of the 4 other carbon atoms, and each of the 4 other carbon atoms shares back only 1 electron with the carbon of focus. Since the carbon atom uses all 4 valence electrons in bonding, there are no unbonded or free electrons on the valence shell of the carbon atoms within the diamond structure. We will now examine a few properties of diamond. Diamond is a non-conductor of electricity because all 4 valence electrons are used in bonding and there are no free or mobile electrons carrying a charge. Diamond has very high melting and boiling points because the structure contains millions of strong covalent bonds between carbon atoms. Therefore, a lot of energy is required to break these many strong covalent bonds. The melting point of diamond is about 3,550 degrees Celsius. Diamond is insoluble in water and organic solvents because there are no attractions between the solvent molecules and the carbon atoms that are strong enough to overcome or break the covalent bonds between carbon atoms. Diamond is one of the hardest substances known. This is so because it would be difficult to break the millions of strong covalent bonds that exist between the carbon atoms throughout the giant covalent structure of diamond. The hardness of diamond makes it useful as cutting and drilling tools such as diamond-tipped glass cutters and as drill bits for oil rigs and rocks. Also recall that the refractive index of diamond allows it to sparkle, which makes it desirable for making jewelry. Next, we will examine the description of graphite. Graphite is a black shiny solid. It is commonly used as lead in pencils and a lubricant because the hexagonal ring layers in the structure easily slide over each other. For emphasis, note that the lead in pencils is not the element lead as in the metal lead, but graphite, which is the element carbon. So graphite, like diamond, is an element of carbon. The graphite structure consists of only carbon atoms bonded together by strong covalent bonds, and each black circle within the structure represents a carbon atom. Within the graphite structure, each carbon atom is joined to 3 other carbon atoms by single covalent bonds, as highlighted in red. This forms a layer of interconnected hexagonal ring layers, that is, 6-membered ring layers. This illustration only shows a few interconnected hexagonal rings. Graphite consists of many millions of these interconnected hexagonal ring layers or sheets. For simplicity, only 2 layers of interconnected hexagonal rings are shown to the left of the screen as highlighted in green and red. The layers are held together by weak forces that allow them to slide over each other, making graphite slippery. So when writing with a pencil, the markings are made as the hexagonal layers slide off onto the surface of the paper. The electron configuration of carbon is 2,4. The diagram of carbon on the left of the screen shows carbon with 4 electrons on its last shell. Keep your attention on this bold carbon in the illustration because it will show what happens with all the carbon atoms within the graphite structure. Within the graphite structure, each carbon shares 1 electron with 3 other carbon atoms. That is, each carbon bonds covalently with 3 other carbon atoms. Each carbon uses 3 of its 4 valence electrons in bonding, that is, 1 with each of the 3 carbon atoms. As a result, each carbon atom within the graphite structure will have 1 unbonded or free electron. These free electrons are delocalized, that is, they are free to move around within the hexagonal ring layer. Now it's time to examine the properties of graphite. Graphite is an excellent conductor of electricity. This is very uncharacteristic of all other giant covalent structures. However, this is so for graphite because each carbon has an unbonded electron that is delocalized. That is, they are free to move around within the hexagonal layers, as illustrated in the animation to the left of the screen. In this experiment, we will demonstrate that graphite conducts electricity. We have set up a simple circuit consisting of 2 1.5-volt batteries, an LED light that terminates with a crocodile clip, and the negative terminal of the battery also terminates with a crocodile clip. Here is a piece of graphite which we obtained from a pencil. As you can see, I'm using the graphite to write. Well, I can't write that beautifully, but at least we know it writes. We will start with a simple control by connecting a rubber band between the 2 crocodile clips to complete the circuit. The rubber band is connected to complete the circuit. Rubber is a non-conductor of electricity, so the LED does not light up. Next, we will complete the circuit using the piece of graphite. Notice that the LED light is on. Therefore, we can conclude that graphite conducts electricity. Graphite has high melting and boiling points because it requires a lot of energy to break the many covalent bonds within the hexagonal ring layers to separate the carbon atoms. Graphite is soft and slippery and can be used as a lubricant because the weak forces of attraction between the layers allow the layers to slide over each other. Keep in mind that diamond and graphite consist of only carbon atoms covalently bonded together, but the structural arrangement of the atoms differ, as you can see in our diagrams of diamond and graphite. So finally, we will examine silica, looking at its description and properties. Silica, which is actually silicon dioxide, is one of the most common minerals in the Earth's crust. Silica can have a crystalline form, which is called quartz, and in our diagram to the left, you can see a sample of quartz. Quartz is found in sand, gravel, clay, granite, and other rocks. Silica can also exist in a non-crystalline form, which is found in glass and silicone. Also note that 1 grain of sand is a giant structure containing millions of silicon and oxygen atoms covalently bonded in the arrangement shown to the left of the screen. Now, these are just a few atoms of silicon and oxygen in this tetrahedral arrangement. However, in 1 grain of sand, we will encounter millions of these atoms in such an arrangement. Now, we will quickly examine the properties of silica. Silica has high melting and boiling points. It's a solid at room temperature. It's a non-conductor of electricity. It's insoluble in water. Here are the lesson summary points. Covalent substances are classified either as simple molecules or giant structures. Simple molecules are either liquids or gases at room temperature. Simple molecules have strong covalent bonds between the atoms within the molecule, but weak intermolecular forces. Simple molecules have low melting points, are insoluble in water, and do not conduct electricity. Strong covalent bonds exist between the atoms within a giant structure. Diamond, graphite, and silica are examples of giant covalent structures. Substances with giant structures are solids at room temperature with high melting points, generally non-conductors, and insoluble in water. Diamond is hard, insoluble, it's a non-conductor, and has a high melting point. Graphite is soft and slippery, an excellent conductor, and has high melting and boiling points. It's quiz time. You have 5 seconds to answer each question after it is read aloud. Question 1. Identify the covalent substance that is an example of a simple molecule. A. Diamond, B. Graphite, C. Water, D. Silica. The answer is C. Water. Question 2. Below is a list of differences in the properties of simple molecules and giant structures. Identify the incorrect difference given for the two structures. A. Simple molecules have strong covalent bonds between the molecules. Giant structures have weak bonds between the atoms within the structure. B. Simple molecules have low melting points. Giant structures have high melting points. C. Simple molecules are gases and liquids at room temperature. Giant structures are solids at room temperature. D. Simple molecules are non-conductors. Some giant structures are conductors. The answer is A. Simple molecules do not have strong covalent bonds between their molecules. They actually have weak intermolecular forces, sometimes called van der Waals forces. And the giant structures have strong covalent bonds between all the atoms within the structure. Question 3. Which statement is incorrect about giant structures? They, A, are solids at room temperature. B, they are insoluble in water. C, they have high melting and boiling points. D, they always conduct an electric current. The answer is D. That statement is incorrect because giant structures do not always conduct an electric current. Question 4. Which property is true for graphite but false for diamond? A. High melting point. B. Conducts electricity. C. Insoluble in water. D. Solids at room temperature. The The answer is B, conducts electricity. Graphite conducts electricity, however, diamond does not. Question 5. Complete the sentence. Covalent substances are classified as A. Simple molecules only, B. Giant structures only, C. Simple molecules or giant structures, D. Electrovalent substances. The answer is C. Covalent substances are classified as either simple molecules or giant structures.
We have reached the end of our lesson. If you found this video helpful, remember to like, share, and subscribe. When you subscribe, you will receive notifications as new videos are uploaded. So until next time, I am Teacher with Iri-e-learning.